Welcome back, architects and engineers. Today we are tackling one of the most persistent dilemmas in retrieval-augmented generation, the chunk size trade-off. We will master how to decouple your search embeddings from your LLM context using parent document retrieval. Let's dive in. Let's begin by defining the core dilemma every AI engineer faces when building a RAG system, the chunk size trade-off. If you split your documents into small chunks, your embedding model captures highly specific details, making your vector search incredibly precise. However, when you pass that isolated sentence to an LLM, it lacks the surrounding narrative to form a good answer. Conversely, if you use large chunks, you give the LLM beautiful, rich context, but the specific details get diluted in the massive text block, causing your semantic search to fail. You are forced to choose between accurate retrieval and accurate generation. Today, we are going to break that compromise. Take a look at this flowchart. Our chunking dilemma splits into two flawed paths. On the left, small chunks lead to high precision but poor LLM context. On the right, large chunks offer rich context but suffer from low retrieval precision. Our goal today is to architect a system that captures the best of both worlds without suffering the drawbacks of either. To solve this problem, we introduce parent document retrieval. The fundamental paradigm shift here is decoupling. We must decouple the text we use to create our search embeddings from the text we pass to the LLM. By using parent-child indexing, we split the document into larger parent chunks and then generate smaller child chunks strictly inside those parents. We use the child chunks solely for generating highly granular, accurate embeddings. But when a search matches a child chunk, we do not send that tiny chunk to the LLM. Instead, we retrieve its much larger parent chunk. This elegant solution guarantees both pinpoint search accuracy and rich, comprehensive context. This architecture diagram visualizes the decoupling process. A single parent document is divided into multiple child chunks. Only those small child chunks are embedded and sent into the vector space for searching. However, notice the arrow coming back. When a match is found, the system traces the child back to the parent document, and it is the entire parent that gets sent as context to the LLM. How do we physically architect this decoupling? It requires a dual store architecture. We cannot shove everything into a single database efficiently. First, we use a standard vector store, like Chroma or FASS, which exclusively holds the embeddings of our tiny child chunks for semantic search. Second, we introduce a document store, typically an in-memory key-value database, to hold the massive parent chunks. The critical bridge between these two disparate systems is metadata. Every child chunk in the vector store carries a unique docID tag. When a child chunk wins the similarity search, the framework reads that docID, queries the key-value document store, and retrieves the massive parent text effortlessly. Observe the schema mapping on screen. In the vector store on the left, we have multiple child embeddings, all sharing the same metadata tag, docID 123. When any of these children are triggered by a user query, a lightning-fast lookup occurs against the document store on the right, instantly pulling the full parent text via that shared ID. Let's move to implementation. To build this, you need to define two distinct text splitters. The first is your parent splitter. This defines your context payload, so you might use a recursive character splitter set to 3,000 tokens, or even an HTML-aware splitter to keep whole chapters intact. The second is your child splitter. This dictates your search granularity, so you might set it to just 500 characters. In code, you initialize both splitters separately. When you pass them into the LangChain retrieval framework, the system handles the heavy lifting. It chunks the massive document using the parent splitter, generates a unique ID, and then passes that specific parent block into the child splitter, ensuring the mapping is mathematically flawless. This process flow illustrates the data ingestion pipeline. The raw document hits the parent splitter, creating a 3,000-character block. Immediately, a UUID is generated for this block. The block is then fed into the child splitter, which slices it into three 500-character child chunks, stamping each one with that exact same UUID. Let's deep dive into the code syntax. LangChain gives us a beautiful abstraction called the parent document retriever. You initialize it by passing in four components: your initialized Chroma vector store, an empty in-memory store for the doc store, your child splitter, and your parent splitter. The true power of this class is in the add documents method. When you call it, you don't have to manually manage the database IDs. The class automatically runs the parent split, runs the child split, links them, embeds the children, and saves both stores. At runtime, when your app executes retriever.invoke, the class silently performs the vector search on the child collection, does the key value lookup, and returns a clean list of parent documents to inject into your LLM prompt. This sequence diagram demystifies the retrieval runtime. The application calls invoke on the retriever. The retriever queries the vector store, which returns the winning child chunks along with their doc IDs. The retriever then takes those IDs, executes a fast multi-get operation against the doc store, and seamlessly hands the massive parent documents back to the application. Let's anchor this in a real-time, high-stakes use case, analyzing corporate compliance contracts. Imagine a legal AI agent analyzing 100-page vendor agreements. The user asks, what happens if a delivery is late? If you use standard RG with small chunks, the vector search brilliantly finds the sentence, late deliveries incur a 5% fee. But because it's just that sentence, the LLM doesn't know which vendor it applies to, the grace periods, or the contract dates. By implementing parent document retrieval, the child chunk triggers the search hit, but the retriever pulls the entire parent section, perhaps the whole 2-page vendor obligations chapter. The LLM now has the exact penalty detail enveloped in its full legal context, empowering it to give flawless, legally sound advice without hallucination. Follow the real-world flow. The query hits the vector search and isolates the specific child chunk about the 5% fee. That child immediately triggers the retrieval of the comprehensive parent section 4. The LLM synthesizes this massive context block, outputting a highly accurate, risk-free legal answer. As we wrap up, we must evaluate the trade-offs like senior engineers. Parent document retrieval is powerful, but it is not free. It introduces storage overhead because you are maintaining both the massive doc store and the heavily populated vector store. Ingestion will take longer as your embedding model processes far more chunks. You must rigorously benchmark the quality improvements against your compute and storage costs before pushing to production. However, for complex enterprise data, decoupling what you search from what you pass to the LLM is the ultimate design pattern for accurate RAG. Thank you for joining this deep dive. I invite learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. This final balance scale visualizes our architectural decision. Parent document retrieval yields immense prose high precision and rich context leading directly to enterprise-ready applications. But we must weigh this against the cons of storage overhead and ingestion time. Master this balance, and your AI systems will be unstoppable.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by quicktechie. We have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see this is all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper, it would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.